Air pollution trade-offs in developing countries, an empirical model of health effects in Goa, India, by Sanghamitra Das, Vikram Dayal, Anand Murugeshan, and Uma Rajaratnam. This presentation is being done by Vikram Dayal of the Institute of Economic Growth, Delhi. I'll now talk about the key features of the study. Air pollution represents the most significant environmental risk to health. 9 out of 10 people worldwide breathe polluted air, with 1 out of 9 deaths in 2012 being attributed to air pollution related conditions by the WHO. Now, in developing countries, both household and industrial air pollution are important, that is, both indoor and outdoor air pollution. So, we need to see the total exposure to air pollution to do justice to the phenomenon. In this paper, we study these different what we call microenvironments: indoor, outdoor, kitchen, and workplace. We examine the association with respiratory health. This study was done in the mining areas of Goa. Our study area was the heavily iron ore mined regions of Goa in India. Iron ore mining was an integral part of the state's economy for almost 50 years and contributed to 60% of India's iron ore exports at the time of the study. Given the scale of iron ore mining in Goa and the documented environmental issues, it was an ideal setting to study total exposure to air pollution. For the purposes of this study, we divided the mining regions of Goa into 5 clusters, including a control cluster, that's cluster 5, with no mining activity at the time of data collection between June 2003 and May 2004. The clusters were chosen to have varying vintage and levels of mining activity. Cluster 1 was the mining region with the earliest mining activity, over 40 years at the time of the study, but where the activity had subsided relative to cluster 2, the most intensively mined cluster, where mining had begun approximately 25 years prior to this study. Cluster 3 was the region where mining activity was relatively at its inception, having begun 15 years prior to the study. Cluster 4 was the mining corridor, that is the region where trucks transported the ore from the mines to the barges or the coast. Cluster 5 was the control region that was away from the mining region and with no history of mining activity at the time of this study. So, in this table, we can see the distribution of villages and the sample size of households and individuals selected for the study. We first selected the regions to represent the levels of mining activity across the state and then randomly chose both the villages and within these villages the households from the census of the households. We surveyed 310 households and 1,411 individuals from these households in the 5 clusters for a detailed assessment of individual and household characteristics, concentrations of pollutants PM10 in the microenvironments, and clinical and reported health measures. The survey questionnaire had 2 modules, household and individual. Both questionnaires were conducted as a personal interview between the enumerator and the individuals, including the head of the household, who also responded to the household questionnaire. The questionnaires were translated into the local language and pilot tested before the actual surveys were carried out by trained enumerators, mostly local social workers. Now look at some of the descriptives by cluster, which is very interesting. So here we have fuel usage, income and air pollution by the different clusters. This is the corridor cluster. These are the three clusters of mining activities there, and this is the control, the cluster which is far away from the mining clusters and where there is no mining going on. In the overall sample, the fuel categories of biomass only, that is this, liquefied petroleum gas only, and biomass and LPG account for almost equal proportions. However, there are sharp contrasts in the shares of fuels among the clusters. As expected, the control cluster, which is a relatively less connected region, has a very high proportion of households, 79%, that use biomass fuels only. In contrast, the corridor cluster, with better road connectivity and where we would expect the highest LPG availability, has the highest proportion of LPG only users, that is 68%. Clusters 1, 2 and 3 exhibited lower LPG usage than the corridor, but higher than the control region, and lower biomass only use compared to the control cluster, but higher than the corridor. The control cluster also had the highest number of kitchens located outside the house, while the corridor had the least. The mean income in the corridor was the highest, lowest in the control region, and the corridor correspondingly has the highest percentage of separate kitchens inside the household, the control the lowest. The income distributions among clusters observed in Table 3 partly explain the fuel usage patterns, where the households with higher income, mining activity regions, had higher usage of clean fuels compared to the control cluster, which had the lowest mean income. We can also see that the outdoor air quality was the worst in the corridor, more than 7 times higher than the control. So 528 versus 71. Due to high LPG usage, the cooking concentration is the lowest among households in the corridor. Note that the indoor concentration will be affected both by outdoor air quality due to infiltration as well as cooking. The high concentration of PM10 indoors among households in the corridor region, despite having the lowest cooking concentration, suggests that infiltration of pollutants from the outside can affect indoor air quality. One of the key features of the paper is this idea of having total exposure, and we shall now illustrate a total exposure calculation for an individual. Now, we constructed the total 24-hour exposure for each individual by computing the exposure in each microenvironment, share of the day spent in the microenvironment times concentration in the microenvironment, and then summed it over all the microenvironments. We measured outdoor at the village level and indoor in the living area of all households, while cooking measurements from a subset were used with information about the fuel choice in the household to get the cooking information concentration. So, here you can see we have a microenvironment indoor. So, for this individual, the concentration in micrograms per cubic meter was 132, the time spent was 12.5. We multiply these two and we get 1650. So, this is microgram per cubic meter hours. The concentration in the cooking microenvironment was 740, time spent was 3, so we get 2220. Outdoor, the concentration was 219, the time spent was 8.5, and so we get this number. For this individual was not working, so neither of these, this is not applicable, the time spent is 0. And so then we sum up the number of hours and we sum up the total exposure, Then we divide this by 24 and we get 239 as the average concentration or the average exposure per hour for this individual. It's basically a weighted average. We also calculated the cumulative exposure to air pollution. The cumulative exposure to air pollution is the total 24-hour exposure to pollutants summed up over the years of residence for the individual in the region as cumulative exposure is equal to total 24-hour exposure into 365 into exposure years, which captures the accumulated exposure to air pollution over the years for each individual living in a particular environment, which determines respiratory health. So, now I will show you a figure which captures the key argument of this paper. So, in the top panels, we see that the distribution of outdoor concentration, that is this, is very different from that of indoor concentration and cumulative exposure. So, this is the distribution of outdoor, this is the distribution of indoor concentration and the distribution of cumulative exposure. When we look at the scatter plots in the bottom panels, so here we have indoor versus outdoor, we can see that there is a very low correlation between the two. Some observations are characterized by high values of indoor concentration and low values of outdoor concentration. This reinforces the claim that using either as a measure of exposure is inadequate. Outdoor concentrations only vary by cluster and would be particularly inadequate, though their measurements would be reasonably accurate. Studies which focus on ambient concentration or household air pollution in isolation may also fail to document the relationship between outdoor and indoor air quality in such a setting. In the other two scatter plots, in the bottom panels, we see that cumulative exposure has a weak positive relationship with outdoor concentration and a relatively stronger positive relationship with indoor concentration. We now look at a two-sample t-test for difference of means in exposure for the 4 mining clusters compared to the control cluster. Outdoor exposure in column 1 is higher in all the clusters with mining activity compared to the control region with no mining activity, with cluster 4 recording the highest outdoor exposure. On the other hand, cluster 3 and the corridor have lower cooking exposure, column 3, compared to the control region due to a higher proportion of LPG usage. The average 24-hour exposure in column 4 is a weighted measure of exposure to different microenvironments and is higher for all 4 clusters compared to the control. We now look at the time spent in microenvironments as elicited in the individual recall survey. The field assistants were able to verify the reported time spent during the household air quality measurements, but this would not completely address the issues with recall methods. Men spent 8.4 hours outdoors on average and women about half of that. Time spent by women in the kitchen on average is about 3.4 hours, while men on average spend less than half an hour. And yet on average, the 24-hour average exposure is 280 micrograms per cubic meter for males and 277 for females. So total exposure balances out on average, in line with this paper's argument that we need to consider microenvironments together rather than separately. I now discuss how we conceptualize our theoretical model that accounts for exposure to air pollution across microenvironments. Yuland et al. In 2015 use a conceptual model to help explain and think about issues in their excellent review of global household air pollution. We develop a model drawing on health production models attributable to Harrington and Portney, 1987, and agricultural household models, Singh et al., 1986, and also a branch of environmental health sciences, total exposure assessment, Smith, 1993. In health production models, health is an outcome of a production function. Agricultural household models try to model consumption and production activities of rural households in developing countries in the same model. Total exposure assessment in the context of air pollution examines pathways from all sources of air pollution to exposure by humans. We view the household model as an abstraction that captures key elements of household air pollution in Goa. There is an obvious element of simplification, and we have noted caveats at different points in the paper. We examine a household which consists of a child, an adult male, and an adult female. We assume that a household aims to maximize its utility, U, which is a function of sickness S, experienced by a child C, the adult male, and the adult female, and non-food consumption C and F. So this is a utility function. We assume that sickness is a function of total exposure to air pollution, consumption of cooked food, doctor visits, and individual characteristics Z. The kinds of sickness that result from poor nutrition and from household pollution are different. The knowledge of or beliefs in causes of sickness of different sorts is a key variable that influences the household's actions. Total exposure is a weighted sum of exposure in different microenvironments, which in turn are equal to the product of time spent in these microenvironments T and the concentrations of air pollution in these microenvironments E. We consider 4 microenvironments in which we have data: outdoors indexed by O, cooking indexed by C, work indexed by W, and indoors indexed by IN. Therefore, EI is equal to this. This is your total exposure. While the time spent in different microenvironments is person specific, the concentrations are not. So that was the basic setup of the model, and essentially in terms of the relationship between activities and choice of cooking and exposure and sickness, one of the key things that is captured by the model is that a change in time spent cooking with LPG or biomass has implication for emissions and exposure and therefore sickness, but at the same time cooking with LPG or biomass affects the amount of cooked food which is available to be consumed, and that too will have a mitigating effect on sickness because it will improve nutrition. And the household also has to balance gathering biomass versus expenditure. So that's the basic message of the model. The details are in the paper. I now will present the results of the analysis. So here we estimate the associations of time spent in microenvironments where we include biomass fuel usage and interact its use with here's the biomass fuel usage and interact its usage with the female dummy along with the individual and household characteristics, as we discussed in theory, where we assumed that only females gathered biomass. The individual level attributes are age, age squared, gender and never smoker, and the household characteristics include the number of adults and children by gender and whether or not the house was pakka, constructed with solid materials as a permanent dwelling. So in this table we have the results of regression on the dependent variables of time spent indoor, outdoor, in the kitchen and at work. We control for cluster level differences by including cluster dummies in our estimation. For time spent in the kitchen, we examine mean time spent in the kitchen by adults in the household. The time adults spend in the kitchen is expected to depend on the composition of adults and children, since one person can cook for several members. We therefore include the number of adults and children in the household by gender in these regressions. So we see that age and gender are statistically significant regressors. Age is related negatively to time spent indoors, shown in column 1, but positively with time in the kitchen, shown in column 3. Males spent less time indoors and in the kitchen. So, males spent less time in the kitchen and more time outside the house or working. Age and education have a positive relationship with time spent working. We call the reader's attention to the positive relationship between biomass fuel usage and time spent in the kitchen in column 3. Also noteworthy is the positive relationship between biomass usage and female dummy on time spent outdoors, which is consistent with the assumption in our models that females spend time gathering biomass fuels. We now look at the household fuel choice. So, here we present the relationship between household characteristics and the choice of fuel, that is biomass only or LPG only. The unit of observation here is the household, and we estimate a linear probability model. As a robustness check, we estimated the models with a binary dependent variable using a maximum likelihood method and find similar results. The dependent variables in table 8 are households who use biomass or LPG for cooking. We include the cluster dummies in the specifications. The regressor Pakka house is negatively associated with biomass only used for cooking, columns 1 and 2, and positively for LPG only, columns 3 and 4, as Pakka house proxies for higher income households. As expected, all 4 clusters are negatively associated with biomass only used for cooking compared to the cooking control cluster. Except for cluster 1, the other 3 mining clusters are more likely to be using LPG for cooking. We now examine the association between cumulative exposure and health. In this table, we present the results of both reported health indicators, respiratory and chronic respiratory sick days, and this is reported health, and clinically diagnosed respiratory health. Experts' diagnosis of the X-ray and lung function test. The respiratory sick days, example laryngitis, sinusitis, pharyngitis, and chronic respiratory sick days, example asthma, bronchitis, wheezing, emphysema, were self-reported by the participants. According to clinical experts, respiratory health measured by X-ray reports is a function of cumulative exposure rather than immediate exposure. As our key variable of interest is cumulative exposure to air pollution, the cardiorespiratory's expert diagnosis of X-rays provides the best measure of respiratory health for our purposes. The pulmonary function test, as clinically measured with the peak flow meter instrument, indicates age-specific lung capacity and can be influenced by immediate 24-hour exposure. So, this presents some of the main results of the paper, the association of health measures and cumulative exposure to air pollution for adults. In addition to the detailed survey questionnaire administered by local enumerators, sampled households were provided with individual health diaries to record the type of ailment, date, number of days sick, number of visits to a doctor, etc. We chose the self-reported sick days for respiratory and chronic respiratory illness as the dependent variables for the results presented in columns 1 and 2. The key variable of interest, cumulative exposure, is statistically significant and positive, indicating a positive association between exposure and respiratory sick days. In all the estimates, we control for individual, age, age squared, education, male dummy, household level Pakka dummy, and cluster dummies to account for fixed effects at the regional level. A 1 unit change in cumulative exposure is associated with a 0.0529 unit change in respiratory sick days. Now, our study has some limitations. Firstly, part of the study uses survey data and the recall method for self-reported health, which is open to measurement errors and biases. Self-reports are amenable to social desirability biases when responding to questions about health. For example, when responding to questions about smoking habits in our survey. Our provision of health diaries at the start of the study to all sampled households could have potentially improved participants' recording and recall during the health survey. Despite our attempts to tie the theory closely to the data collection process that allowed us to apportion exposure to pollution sources, we were still limited in our empirical strategy by the data. Our measure of cumulative exposure assumes that the current 24-hour exposure is indicative of exposure across the years for the individuals living in the location. But pollution levels could have varied considerably over the years in the locations which we do not account for in our exposure construction. Similarly, we do not measure cumulative smoking years of individuals. Moreover, we measured PM10 rather than PM2.5, which could arguably be a better indicator of respirable pollutants. We only measured particulate matter concentrations, while health is also impacted by other noxious matter, example sulfur oxides. We'd like to point out that sophisticated treatments of costs and benefits have been published since the data collection for this study, notably a study by Yulin et al. In 2015A. Our particular contribution is the incorporation of total exposure and microenvironments. Air pollution valuation studies may to some extent abstract from total exposure or at times simply ignore household air pollution. Now discuss conclusions. Our study develops an integrated empirical model to study the association between respiratory health and total air pollution. The two distinct features of this paper are proposing an integrated empirical model of health effects of air pollution and using disaggregate data on exposure in different environments to test the empirical implications from the model. The delineation of exposure levels from different microenvironments offers insights into the comparative magnitude of impacts from both household and outdoor air pollution. This approach has allowed us to examine the relationship between respiratory health and household and outdoor air pollution together. In our empirical analysis, we examine the association between individual characteristics and time spent in different microenvironments, the distribution of concentrations in the microenvironments among clusters, the relationship between clusters and household fuel usage, and the relationship between cumulative exposure to air pollution and health outcomes. To highlight, we found that biomass use was positively associated with time spent in the kitchen, which may be due to the lower efficiency and higher cooking time associated with biomass fuels. B. There is a positive association between outdoor air pollution and LPG usage, negative between outdoor and biomass use, which along with associated results on the cluster dummies implies that regions with mining activity had a higher likelihood of LPG usage. Cumulative exposure is positively related to biomass fuel usage, time spent in the kitchen where biomass fuels were used, household and outdoor air quality, and cumulative exposure to air pollution is positively associated with self-reported and clinically diagnosed respiratory issues. Our results emphasize the findings in several studies that household air pollution from traditional cooking pollution technologies adversely affects respiratory health. We find that switching from traditional biomass cooking to LPG stoves is associated with a substantial reduction in cumulative exposure, which is similar to findings in the literature on fuel switching. Findings from such a cross-disciplinary team can offer several direct implications for policy making. We chose a setting with a recognized outdoor air quality problem, a heavily mined region in India, to study the relationship of both outdoor and household air pollution with health. Our design and data allowed us to compute total exposure to air pollution as an outcome of air quality and time spent in the microenvironment. Thus, policy should not just focus on improving cooking technology and fuel choice, but also provide information that improves time allocations in polluted environments, including household kitchens. In rural areas of developing countries, particularly in households using biomass fuels and poor kitchen ventilation, household air pollution is a relatively more significant health hazard. So, the bottom line is that we have seen household air pollution, we provided a proof of concept of this integrated empirical model, and apart from the measures that are used in mining areas to control outdoor air pollution, we also recommend that indoor air pollution be given some attention. Finally, we'd like to point out that a paper which has appeared recently after our paper was written, called Health Awareness in the Transition Towards Clean Cooking Fuels, Evidence from Rajasthan. So, this is a paper in which the authors examined in a field experiment in Rajasthan the role of health messaging. And so, one can then look at what influences the switching of households to LPG, and in this field experiment they directly examined the effect of health messaging on the adoption of or the willingness to pay of households for using LPG, and also how much households actually increase their use of LPG.